Hello, Chem 1132. This is Mr. Coker, and this is the long-awaited Chapter 20 notes. Chapter 20 is a extension of Chapter 19. In Chapter 19, we looked at the S and P block of the periodic table, which are called the representative elements. In Chapter 20, we're going to look at the D and the F block, which are the transition metals. One important part of the transition metal chemistry is its ability to form coordination compounds. So these are the 8 sections. First, we'll survey the transition metals. Then we'll look at the first row of the transition metals as an example. We'll look at what coordination compounds are, how they can form different kinds of isomers. In 25, we'll look at how the bonding in complex ions can be explained with the localized electron model, and then we'll look at the crystal field model, which does a little better job of explaining the bonding in complex ions, and especially justifying the colors that we see in complex ions. And then we'll look at some examples of coordination complexes in biology, and then look at how metallurgy, iron, steel production are important aspects of the chemistry of metals. So first, let's survey the transition metals. We find that the transition metals have a lot of similarity within a given period and also within a given group. The chemistry of the transition metals elements are not as affected as you change the number of electrons in the atom as they are in the representative elements. In the representative elements, we see changing from noble gases, which lose electrons easily, or from alkali metals, which lose electrons easily, to noble gases, which are very difficult to remove electrons from. As we move left to right across the periodic table, each new electron gives a kind of a different chemistry, which is why we have the different families and groups. However, with the transition metals and the transition elements in the D and the F block, we are not adding electrons to the valence shell. The D and the F block, the D and the F sublevels are inner sublevels. So for example, in the 3D, before you put any electrons in the 3Ds for scandium, titanium, vanadium, and that row of the periodic table, before you add the 3D electrons to an atom, you have already begun the 4th energy level, because the first 2 elements in the 4th row are filling the 4s. And so the 4s has already begun, and the 4s is considered your valence electrons. And then you're going back and you're putting more electrons in the 3rd level. But because that is an inner portion of the atom, the extra electrons effectively just cancel out the extra proton you're adding, because they create a shielding effect for the valence electrons. And so you're adding a proton, which is pulling the valence electrons tighter, but then you're adding an inner electron, which is pushing the outer electrons away, and the effect is sort of a stalemate, and there's really not much difference as you add electrons to the atoms, because they're effectively canceling out the effect of adding protons. So the fact that they are inner electrons for the D block transition metals, and then also the F electrons are 2 levels down for the lanthanide and the actinides in the inner transition metals. And since those D and F electrons are not typically going to participate as much in bonding as the valence S and P electrons, the transition metals and the inner transition metals, the D and the F block, show a lot of consistency in their properties. So this is a part of the periodic table we're talking about. This D block would be this yellow area, and then the F block would be the lanthanides and the actinides. I like to call them the inner transition metals, and the D block the transition metals. So one of the main characteristics of these transition metals is that they can form more than one oxidation state. So, for example, iron can be +2 or +3 in an ionic compound. Copper can be +1 or +2. So that's one of the main things to remember about the transition metals is their ability to form more than one oxidation state. Also, the cations can also form these complex ions by forming connections to ligands, which use are Lewis bases that will bond to these ions and create these complexes, these combination things, which would be a transition metal cation connected to molecules or ions that are acting as Lewis bases. We call those ligands. And these can be as many as 6 molecules or ions surrounding a center atom, connecting to that center ion using their unshared pairs as bonds, forming coordinate covalent bonds with the cations. So these would typically occur in water solution. Examples we see here are the cobalt with 6 ammonias attached to it. So 6 ammonias surrounding it in an octahedral geometry. Because ammonias are neutral and the cobalt is +3, the entire complex ion would be +3. Then you would probably have some counter ion with it. This particular compound says that it has 3 chlorides. So 3 -1 chlorides would balance the +3, and the chloride anions would be the counter ion to the cobalt with 6 ammonias coordination compound there. A lot of these compounds are colored, and we're going to talk later about how those colors form. Many of them are also paramagnetic, meaning they contain unpaired electrons, and that's also an aspect of the bonding that occurs in using those d orbitals. Let's start by kind of surveying the first row of the transition metals, the scandium through zinc group. These are atoms that are filling the 3D sublevel, and you can consider them to be representative of the other transition series. What we're seeing by looking at scandium through zinc, a lot of that same information translates to the next row down, the next row down. These 10 atoms or elements, scandium through zinc, have a lot of practical significance. They're used in a lot of different applications. So we're filling the 3D orbitals, but they're beginning to fill after the 4s orbital is complete. So the first metal, scandium, would be 1 electron in the 3D, so that would be 4s2 3d1 with an argon core. The second metal, titanium, 4s2 3d2, vanadium would be 4s2 3d3. So we're seeing a pattern here of putting one more electron in the 3d. The next atom, chromium, though, is the first atom on the periodic table that doesn't follow the electron configuration pattern perfectly. You would expect chromium to be 4s2 3d4. But instead it's 4s1 3d5, and that's because the 2 electrons in the 4s have more repulsion than if you simply move one of them to the empty 3d orbital, the 5th 3d orbital that doesn't have an electron in it. So 4s1 3d5 spreads the electrons out more evenly than 4s2 3d4. So as a result, we see chromium having an exceptional or an exception to the rule electron configuration. Copper also has a similar situation. So instead of being 4s2 3d9, copper is 4s1 3d10. So this page kind of summarizes, if you want to pause this and look at in more detail, but it summarizes the atomic numbers of scandium through zinc, the electron configurations, the atomic radius, the ionization energies, first, second, and third, and reduction potential, which we look at when we go into electrochemistry, common oxidation states, melting points, densities, and electrical conductivities. When it comes to some of the physical properties such as density and atomic radius and melting point and things like that, we see quite a bit of similarities, quite a bit of consistency. We do see with scandium and zinc that their atoms are bigger, and as a result their densities are less. So they are not only the lightest elements in this row of 10, they're also the largest atomic radius. And so that's why they have lower density than the ones as you go to the right, which typically end up in the 7 or 8 grams per cubic centimeter. The 3D orbitals are significantly less in energy than the 4s, at least for scandium and zinc, and for scandium and titanium in the early ones they are. I believe as you go closer to zinc, they actually, the gap between the 3D and the 4s does shrink a little bit. The first row transition metal ions don't have 4s electrons in ion form. And so what we're seeing with the first row transition metal ions is when they form ions, they're going to lose their 2 4s electrons and then possibly also some of the 3d electrons. So for example, neutral titanium is 4s2 3d2, but the cation, one of the typical cations for titanium is titanium plus 3. That would be argon 3d1. You would lose the 4s2 and one of the 3d electrons to get the 3 plus charge. Manganese, which is 4s2 3d5, when it loses 2 electrons to become manganese 2, is just 3d5. So notice it loses the 4s electrons. So what would we expect the electron configuration of scandium plus to be? So since we don't have the 4s electrons, if it's only plus 1, then what we would see is the other 2 electrons that scandium has would be in the 3d2. For the first 5 metals, the maximum possible oxidation state is going to correspond to losing all the 4s and all the 3d electrons. So for example, chromium can go all the way up to a plus 6 for its oxidation number. So that would be losing the 4s1 and the 3d5. So that would be a plus 6 oxidation number for chromium. Manganese can go to plus 7. But scandium, maximum possible oxidation state would only be plus 3 because of its 4s2 3d1 arrangement. Losing all the 4s and 3d electrons, there's only 3 to lose. So that's why it would be plus 3. The plus 2 ion is the most common for these, particularly as you go to the right side of the period, and that's because the 4s electrons are the most easily lost. So the 4s2 are lost and you get a plus 2 ion. Typically as you get to the right of the middle of the D block, you don't see losing electrons from the 3D as much. So you don't see the higher oxidation states than just plus 2. So what you see here is the first ionization energy for scandium through zinc, which you see is fairly consistent compared to the third. For the third ionization energy, in other words, the 3d electrons you lose after you lose the 4s, they're easier to lose for the first 5 than they are for the last 5. Iron's sort of a exception there because iron being 4s2 3d6, you can lose the 4s2 and iron can form a plus 3 ion by losing one of its 3d6 electrons. The reason why it would want to lose that 3d6 electron is in order to get rid of repulsion because of one of the d orbitals being double filled. By losing one electron, it can go to 3d5 and everything is half filled. But for zinc, obviously with a very high third ionization energy, zinc's going to be plus 2 and never plus 3. This is the reducing abilities of the first row transition metals. This is their reduction potential, which we talk about in electrochemistry. Scandium is the highest reduction potential, and copper has the lowest reduction potential. When you compare the elements in the 4D and the 5D transition series, you want to look mainly at the atomic radius. There's a general decrease in size going left to right for the 4D and the 5D, but from 3D to 4D, there's a larger increase in size as you go down the chart than there is from 4D to 5D. The 4D and the 5D are very similar in size. The reason why the 4D and the 5D are very similar in size that is because of the 4f orbitals that get filled up before the 5D transition metals occur. The filling of those 4f electrons in the lanthanide series generally means that you're not going to see as big of a difference in size because there's some shrinkage as you fill those 4Fs, and that shrinkage kind of cancels the effect of the extra energy level from 4D to 5D. We call that the lanthanide contraction. So the 4D and the 5D actually have very similar chemistry because they have very similar atomic radius. This graph illustrates the lanthanide contraction. You see a fairly decent gap between the green, which is the 3D atoms, and the blue, which are the 4D atoms. Fairly significant gap there in size. The 3Ds are smaller than the 4Ds, but the red and the blue are almost right on top of each other. In other words, the 4D and the 5D are very similar in size due to the lanthanide contraction. That's because the 5Ds have the 4f electrons that precede their filling. So looking at the first row transition metals, scandium, its chemistry resembles a lot of the chemistry of the lanthanides, being colorless and diamagnetic, and it's going to look a lot like the lanthanides. Titanium is an excellent structural material. We find it alloyed with alloyed with aluminum in airplane parts because it's light and strong, low density and high strength. Vanadium is used in a lot of alloys. It can be alloyed with iron and various steels and alloyed with other elements, other metals. Chromium, very important industrial material. We see chrome put on the surfaces of things in order to resist rust. Manganese is used in producing very hard steel. Iron, this is the most abundant and the most used of the metals, and we see iron used in steel production, and steel production, of course, is a big part of any technologically advanced culture's economy. Cobalt is used in alloys such as stainless steel. Nickel, often used for plating over metals that you don't want to rust, and also used in the production of alloys. Copper has plumbing for copper piping, and also copper wires used in electrical applications. And the main use of zinc is for coating steel to avoid rust. It's called the galvanizing steel. The zinc oxidizes instead of the iron, and so it protects the iron from rusting. So if you've heard of galvanized nails or galvanized roofing, it's steel coated with zinc. Various oxidation states for transition metals can have various colors. So we see some oxidation states for vanadium here and what colors it would produce in water. Here are some chromium and chromium compounds, and various colors that it has with different oxidation states and different counterions. Here we see manganese and manganese colors. often in the pink part of the spectrum. Here are some iron colors. Iron can be anything from brown to black to green to yellow to red, even blue. Cobalt, blues and pinks and reds and greens. Nickel can have a lot of different colors to it. Of course, with copper, we see copper can be blue or green in water with the +1 and the +2 oxidation state. Copper is found in a lot of different alloys: brass, bronze, sterling, silver, gold alloys. Copper has different colors depending on its oxidation state and what it's bonded to. So let's get into this section on coordination compounds. Coordination compounds, I mentioned earlier, are when the transition metal ion, cation, is bonded in water with molecules or ions that are going to bond using Lewis acid bonds, with the Lewis base donating an electron pair to form a bond to the cation, the transition metal cation. These form coordination compounds. We have our center ion, and then the molecules or ions that attach to that center ion are called ligands. You also have counter ions, which are the anions or cations needed to balance out the charge so there's no overall charge. So here we see how they typically would write the formula. We see a cobalt, which would be your transition metal cation, in this case +3. We see that it's bonded to 6 ligands, 5 of which are ammonia, and 1 is a chloride ion, a Cl- ion. And so the cobalt bonded to the 6 ligands, that's all within a square bracket there. And then outside the square bracket, we see the 2 chlorides, which are the counter ions to the cobalt, which is +3. And then you have the Cl- inside the brackets. So the whole complex ion, cobalt with 5 ammonias and 1 chloride, has a +2. And then you have the Cl2 outside, which are -2. Here we see iron, and it's bonded to 2 ethylene diamines, abbreviated En. It's also bonded to 2 nitrites, NO2 minus ions. And then the whole thing has a +2 charge. And so sulfate -2 is the counter ion. Then we have 3 potassiums, which would be the counter ion to the iron bonded to 6 cyanides. So the iron would be +3, the 6 cyanides would each be -1, and then the potassium would each be +1. And so you see with the potassium and the iron, you've got +6, and with the 6 cyanides would be -6. The number of bonds between the metal ion and the ligand is called the coordination number, and it can go anywhere from 2 to 8 depending on the size of the cation and also its charge and how much charge it has, and then the electron configuration. 6 and 4 are the most common. 2 would probably be least common. Many metal ions show the possibility of forming different complex ions with different coordination compounds. So copper could have a coordination number of 2 or 4. So can copper 1 does. Gold 1 can be 2 or 4. Copper 2 could be 4 or 6, and so forth. If you have 2 coordination numbers, in other words, if the central cation is bonded to 2 ligands, they will typically bond in a linear geometry. If you have 4, they could bond tetrahedral or square planar, depending on exactly how the bonding takes place, and we'll get into each of those later. If you have a coordination number of 6, you're typically going to be octahedral. The ligand is a neutral molecule or an ion with a lone pair of electrons that can form a bond to the metal ion. That type of bond is called a coordinate covalent bond, where we get the term coordination compounds. It's the metal ligand bond resulting from the Lewis base, which is the ligand, and the Lewis acid, which is the metal ion. If the ligand forms one bond to the metal ion, it's called a monodentate ligand. If it forms two, it's a bidentate ligand. And you can even have ligands that can form more than two. Once you go above two, we call it polydentate. Dentate actually comes from the idea of teeth and how it can, like, the teeth can clamp down on the cation. The ligand can kind of clamp onto the cation with one set of teeth or two set of teeth or whatever. Here we see an example of a bidentate ligand, ethylene diamine. Ethylene diamine is a single molecule, NH2, CH2, CH2, NH2, but with two N's, two nitrogens, and each nitrogen having an unshared pair, a lone pair, you can actually bond to your metal, your transition metal cation in two different locations. So we call it bidentate. This would be a monodentate ligand, such as ammonia. With only one unshared pair, it's a monodentate ligand. This is an example of a polydentate ligand, ethylene diamine tetraacetate, and we're actually, in this case, bonding multiple places here. We can tell we're bonding at multiple places to the metal ion. In fact, I think EDTA might actually be hexadentate and bond octahedrally in 6 different locations to the metal ion. Now, the rules for naming the coordination compounds are a little different than ionic compounds, but we do have the similarity that you have the cation named before the anion. But in naming the complex ion, you're going to name the ligands before you name the metal ions. So in that case, it could be you're naming the negative part before the positive part in the complex ion portion of the coordination compounds. If your ligand is an anion, you're going to change its ending from "ide" to "o". So instead of fluoride, you say fluoro. Instead of cyanide, you say cyano. Hydroxide, hydroxo. For the neutral ligands, we simply name the molecule. So H2O, water, or you might use a Latin word like aqua, NH3, CO, NO. We're going to name it by the molecule. We do see the prefixes mono, di, tri, tetra, penta, hexa used to denote how many ligands, simple ligands, are attached. And for places where maybe there are 2 pairs, you might see bis or tris or tetrakis used so that you're not repeating the prefix, the same prefix. Bis would be 2, tris would be 3, tetra would be 4. Oxidation state of the metal ion is designated with a Roman numeral in parentheses, just like it would be if it was not a coordination compound. And when you have more than one ligand present, you name them alphabetically. So do the first one in the alphabet first. Prefixes do not affect the order. It's the alphabetical nature of the name of the ligands. When your complex ion has a negative charge, instead of saying something like iron 3, we put the suffix "ate" on the Latin name. So iron would be ferrate, copper would be cuprate, lead would be plumbate, and so on. So to illustrate this, that's a lot of rules. So to illustrate it, let's do these compounds here, these coordination compounds. We see a cobalt transition metal bonded 5 times to ammonia and once to chloride, and then it has 2 chloride counterions. In B, we see 3 potassium plus 1 counterions bonded to the complex ion with an iron plus 3 surrounded by 6 cyanides. And then we see C, we see the iron with 2 ethylene diamines and 2 NO2s and a sulfate counterion. So to determine the oxidation state of the metal ion, we have to kind of look at the charges of all the ligands and the counterions and figure out what would balance that out. For the first one, ammonias are neutral and chlorides are -1. So your cobalt's going to be +3 because it has 3 chlorides and 1 cobalt. 1 chloride is a ligand, but the other 2 are counterions. So our cobalt's +3, so we're going to call it cobalt 3 with the 3 in Roman numerals and in parentheses. The ligands are 1 chloride and 5 ammonias. The chloride is called chloro, and the ammonias are called amine. We use the prefix penta because there are 5 ammonias. And we put the ammonias first because of alphabetically A comes before C. And remember, you name the ligands before you name the transition metal ion, and then finish with the name of the counter ion. So here we see pentaamine for 5 ammonias, chloro, cobalt 3, and then chloride. So pentaamine, 5 ammonias, looking here in letter A, chloro for the Cl, cobalt 3 because cobalt has a +3 charge in this formula, and then your 2 chlorides are just called chloride. In the second one, we have the 3 K plus ions. So since they come first, they're going to be named first, potassium. And then we also have the Cn minuses, which are cyano. And hexa would be our prefix. And then because the iron is part of a negative complex ion, we're not going to call it iron 3, we're going to call it ferrate. So potassium hexacyanoferrate would be how we would name it. And then the last one, we've got the 4 NO2 minus ions, the SO4 minus 2 ions. The ethylene diamine is neutral, and so the iron is +3 in this case. Ethylene diamine, so the iron is +3. Notice there are 2 of the complex ions for the sulfate. So 2 +3s, or actually, yeah, I think that's maybe a misprint. The 2 maybe should have been, I'm trying to add up these charges here real quick. Okay, so there are 2 NO2s. Okay, let me catch up here. 2 NO2s, each one -1. The ethylene diamine is neutral, so the iron and the complex ion is a +1. And there are 2 +1s to go with the sulfate, which is -2. Okay, so our name is going to be bis ethylene diamine in order to avoid saying di twice there. Bis ethylene diamine, dinitro, the nitride becomes nitro, iron 3, and then sulfate, the counterion. Going the other direction, maybe we can kind of figure out how to take apart a name. Triamine would mean 3 ammonias, bromo would be 1 bromine, platinum 2 would be PT, So the complex ion would be PTNH33Br. The PT would be +2 and the Br would be -1, so the complex ion would add up to +1. And then a chloride, you would have 1 minus 1 chloride to go with it. So your formula would be PTNH33Br in brackets and then Cl. These complex ions can form different kinds of isomers. Isomers are when you have the same formula but a different geometry. And the different geometry can give it different properties. There are structural isomers and then there are stereoisomers. First, looking at structural isomers. Structural isomers have things bonded to different atoms. You can have coordination isomerism and then linkage isomerism. For stereoisomers, which they have the same bonds but maybe a different spatial arrangement, you can have geometric isomers such as cis and trans, and then optical isomers. So coordination isomerism would be maybe switching the counter ion with one of the ligands. So if you've got chromium and 5 ammonias and a sulfate as a ligand and a bromide as a counter ion, that would be a coordination isomer to chromium with 5 ammonias and a bromide as a ligand and a sulfate as a counter ion. So the bonding is actually different. In one, the sulfate's bonded to the chromium, in the other, the bromine is bonded to the chromium. Linkage isomers would be because you have different points of attachment around the center ion. You can have different places that they link up around it. So maybe they're still bonded, the same bonds, but the bonds are in different places. So an example of that would be if the NO2 minus ion used the nitrogen unshared pairs to bond to the cobalt, or alternatively, it could use the oxygen unshared pairs to bond to the cobalt. And so we have a coordination isomer there. Stereoisomers, we have all the same bonds, but spatial arrangements. Geometric isomers such as cis or trans, cis being side by side, trans being opposite. So here we see in a platinum with a square planar arrangement, if you put your ammonias and your chlorides where they are next to each other, the same ones next to each other, that would be called cis. And that is actually a darker yellow color than if you put your chlorides across the square planar arrangement from each other and your ammonias across, which would be called trans. That's actually more pale yellow. So it has different properties because it has different spatial arrangement of the bonds. And here we have 4 ammonias and 2 chlorides. If your 2 chlorides are across from each other, that would be called trans. If your chlorides are closer to each other and only 90 degrees apart, that would be called cis. That's another example of cis and trans. Trans being across, like transatlantic flight, you go across the ocean. Optical isomerism is where you see, if you have some polarized light passing through the chemical, you'll actually see that it rotates the electric fields of the photons in different ways, and that's called a geometrical isomer. Well, actually, it's called optical isomerism, or chirality is another term that they sometimes use for that. So the effect would be that the light source would be unpolarized, then passing through a polarizing filter, it'd be polarized, and then that polarized light would be rotated in one angle or another, opposite either to the right or to the left, by interacting with the different isomers, either the right-handed or left-handed isomers. So we call this chirality, and it's effectively the molecules are similar to our left and our right hand. Our left and our right hand are basically in all ways identical, except that they're not superimposable. You cannot put your left hand on your right arm and it look the same. The thumb would be pointing the wrong way. And your left hand is basically your mirror image of your right hand. It's not the same as your right hand, it's a mirror image of it. So we call that chirality, and we call the two enantiomers. If it rotates the plane of light to the right, it's called dextrorotary, or D. If it rotates to the left, it's called levororotary, or L. A racemic mixture would be an equal mixture of D and L, which would not rotate the plane of light because the D and the L cancel. So let's take a look. If we had cobalt and we had one ammonia, one bromine, and two ethylene diamines, and they form a +2 complex ion, would we see some geometrical isomerism? And if so, would it have optical isomerism? So if we look at how we can arrange them, we could put the bromine and the ammonia and the two ethylene diamines, which are bidentate, we could put them across from each other in a trans arrangement, or we could put them next to each other in a cis arrangement. So we would have cis or trans. So we have the cis and the trans. The cis isomer would actually also have optical isomerism, because if you look at the two images here, both of them, the cis isomer, they are mirror images and not superimposable. So as a result, the cis isomer does show the optical isomerism of being able to be chiral. The transform does not. Okay, so looking at different ways we can explain the bonding of these complex ions. One way would be to attempt to explain it with the localized electron model. If you remember from first semester, the localized electron model uses VSEPR to explain the geometry. So that would be looking at the coordination number of 6 would be octahedral, the 4 could be tetrahedral or square planar, the 2 would be two ligands would be linear. That would be ways of keeping things as far apart as possible. And what you would be explaining that with would be, you would be saying that the metal has these hybrid atomic orbitals that it's using to overlap with the lone pair orbital on the ligand to make the coordinate covalent bond. So here we would see cobalt with a geometry of octahedral would be D2sp3 in order to get the octahedral orbitals, and then the nitrogen would use its sp3 orbital to form the coordinate covalent bond. For the tetrahedral, we would have sp3. The arrangement we would need for the square planar would be dsp2, and then for linear we would just have sp. The crystal field model is a little different and a little bit more effective at explaining the magnetism and the colors of these coordination compounds. So in the crystal field model, what we're doing is we're assuming that the ligands, which we're approximating as negative point charges, are interacting with the d orbitals on the metal ion. So remember, the d orbitals can be dxy, dxc, dyz, dx squared minus y squared, and dz squared. And so we're sort of looking at it as a metal ligand bond being ionic. So the principle would be, since these are the geometries for dxy, dyz, dxc, and dx squared minus y squared, particularly for um, something that was, let's say we have something that is octahedral. Octahedral would be interacting directly with the dz squared and the dx squared minus y squared. But the dxy and the dyz and the dxz would not be pointing at the octahedral positions. So that actually changes the energy of the dz squared and the dx squared minus y squared, so it's different than the dxc, the dyz, and the dxy. So now, instead of all 5 d orbitals having identical energies, we see a splitting, we see a raising of the dz squared and the dx squared minus y squared. In comparison, we see an energy gap between that and the dxz, dyz, and dxy. All of them are going to be higher than the energy of the 3D orbital without the ligands, but we're going to see a larger increase in the energy of the ones with the squares on them. That gap, that energy gap, is going to explain the colors of the light that is absorbed by these transition metal ions. These two sublevels are designated EG and T2G, and they are the splitting into two different groups of the D sublevel. So, like I said, this explains color and explains magnetism for these complex ions. The strong field example, which is also the low spin example, is when your ligands interact strongly with the d orbitals, and you get a large splitting between the T2G and the EGs. And as a result, when the electrons enter the d orbitals, they are going to double fill the T2G before they start adding electrons to the EG. So they're going to act like they're different sublevels. And that's why you don't have as much spin, because you don't have as much unpairing in that case. So we call it the low spin case. So these are going to typically give you something that's diamagnetic instead of paramagnetic, and you're going to have the minimum number of unpaired electrons. The weak field case is if your ligand does not interact strongly with the d orbitals. The small splitting of the d orbitals will actually mean that all 5 orbitals will sort of fill with 1 electron each before double filling. So that'll give you more unpaired electrons, which would be more likely to be paramagnetic, the weak field case. So the strong field case is where you have a large splitting of the T2G with the EG, and the electrons are more likely to pair up, compared to the weak field case, where you have a small splitting between the EG and the T2G, which as a result you follow Hund's rule and put 1 electron in each before double filling. So you get the diamagnetic example. So if we take a look at chromium with 6 cyanides and a 4 minus charge, and then predict how many unpaired electrons there are, we need to look at, first of all, the 4 minus charge means the chromium is +2, 6 negatives and 2 positives would add up to -4. And that means that the chromium being +2 would have a 3d4 electron configuration, because it would lose the 4s and one of the 3d electrons, because remember chromium's that exception 4s1 3d5, so you lose the 4s and one of the 3ds. So 3d4 means 4 electrons in the d orbitals. Now we ask, is cyanide going to be a strong field ligand and cause a large splitting, or is it going to be a weak field ligand and have a small splitting? So if we look at the charts on cyanide, which there's a chart in your book, cyanide is a strong field ligand, meaning a large delta or a large splitting. Since that's a large splitting, we are not going to put an electron in the EG until we totally fill the T2G. So it's going to act like the S and the P. The S fills up before the P starts. So with 4 electrons, you're going to have 2 electrons paired and 2 individual. So you're going to have some diamagnetism, or paramagnetism rather, paramagnetism because of the unpaired electrons in the T2G. So with 2 unpaired electrons, we have the strong field case where the cyanide ligand forming the large splitting results in some paramagnetism. So this chart here shows the strongest of the strong field ligands and then the weakest of the weak field ligands in order here, starting with cyanide and then ending with iodide. So you might refer to that if you have a case of having to decide if something is the paramagnetic example or the diamagnetic example. Something else is that splitting is going to be the delta E that determines the wavelength of light that is going to be absorbed by that particular complex ion. Remember that the energy absorbed is the energy to move an electron from, in this case, the T2G up to the EG, and that delta E is going to equal Hc over lambda. And so the larger the energy splitting, like a strong field case, you're going to have a smaller wavelength that's going to be absorbed. Now, you won't see that color. You'll see the color that's complementary to the absorbed color. The color then will change as you change ligands. Different ligands will split that energy different amounts, and so you'll get different colors depending on what ligand you have and whether it's a strong field or a weak field ligand. So we see in the case of titanium with 6 waters plus 3, you've got your T2G electron for titanium that's going to be promoted up to EG with the absorption of a wavelength or a photon of light. If your complex ion absorbs 400 nanometers, which is a violet color, the color you'll observe will be a greenish yellow. If it absorbs, say, 600 nanometers, you would actually, which is orange, if you absorb the orange color, you see the blue color, the complementary color. So then you can go through and you can analyze different complex ions that are possible and which ones will form colorless and which ones would form colored. Now in the case of Zn plus 2, you actually have a 3D10 arrangement, and with a 3D10 arrangement you also have that with copper plus 1. You have a, because the copper plus 1 is 4s1 3D10, and then you lose 1, it'd be just 3D10. The 3D10 arrangement, there is no ability to have any movement of electrons within the d orbitals because they're already full. Same thing with the silver plus 1. Titanium plus 4, you would not see any color because you have no electrons in the d orbitals because you've lost the 4s2 and the 3d2. The others would all have examples where there are electrons in the d orbitals, and so there's some movement of electrons between the T2G and the EG, so you'd have color. In the tetrahedral arrangement, none of your 3D orbitals are really going to line up, and so you're not going to see as much splitting in a tetrahedral arrangement of splitting of the different energies. The d orbital is going to be, splitting is going to be opposite what you see with the octahedral. So you're always going to see the weak field case because you don't have as much splitting of the T2G and the EG. And that's just because the way the geometry of the tetrahedral doesn't really have effectively any difference in how it interacts with the dz squared, dx squared minus y squared, or the EG orbitals. compared to the T2Gs, which are dxy, dxz, and dyz. So just to illustrate this, in an octahedral case, there's more splitting. In the tetrahedral case, it's actually inverted. dxy, dxz, and dyz, the T2Gs are higher, but not very much higher. It's a weak field case. So looking at the crystal field diagram for cobalt tetrachloride here, tetrahedral complex ion, the cobalt will be 3d7, which means 7d electrons, and you're going to fill up the two lower ones and put one in each of the three upper ones. So you actually are going to have some paramagnetism with it in that case. So considering the crystal field model, which is lower in energy, the d orbitals, lobes pointing toward the ligands or between, it's actually the, looking back here, the lower energy d orbital lobes would be the ones between. So this is a misprint here. The square blue box should be around the between. And because it's because they have less interaction, is that they are lower in energy. And then the d orbitals are from the metal, so that's correct. So A is actually incorrect. That box should be around the between, not around the toward. If you have electrons choosing to pair up in the d orbitals instead of being in separate orbitals, that's because you have the high spin case or the strong field case. The predicted splitting in the tetrahedral complexes is smaller than in the octahedral complexes because you have less interaction. Nothing really lines up. The d orbitals don't really line up with the tetrahedral positions. So sketching some possible electron arrangements, this would be the nickel +2 ion. So ammonia is I'd say a strong field ligand. So the nickel would be, let's see here, doesn't do it, does it? So the nickel, nickel comes right before copper, so it's 4s2 3d7, I believe. Go back to where it talks about electron configurations. Sorry about this, going way, way back. So nickel, 4s2 3d6. 4s2 3d6. I'm sorry, 4s2 3d8. 4s2 3d8. Sorry about that. Getting close to finishing up. All right, so we're 4s2 3d8 prior to losing 2 electrons. So that would make us 4s2 3d6. If we have the strong field case, then all the electrons would be paired up in the T2G, the 3 lower orbitals. And so we would have no electrons in the EG and 6 electrons in the T2G. That's what our sketch would look like. FeCN6 3 minus, the 6 cyanides are -6, so the iron would be +3. So iron plus 3 would be, okay, iron 4s2, 3d6. Iron plus 3 would be 3d5. Cyanide's definitely the strong field case. So 5 electrons would be 2 pairs and 1 single in the T2G would be what we'd have. Nothing in the EG. Cobalt, ammonia, 6 plus 3, that'd be cobalt, which is 3D3, 4s2, 3D3. And then 3 plus charge would be 3D2. So with 3D2, you'd only have 2D electrons, and so you put 1 each in the T2G. Okay. A metal ion in a high spin octahedral complex has 2 more unpaired electrons than the same ion in a low spin. So 2 more unpaired electrons. So the possible metal ions would be something either D4 or D7. So D4, you would have all 4 unpaired in the high spin case, and then a pair and 2 individuals in the low spin case. And so D4 would be an example. D7 would also work because you would have 2 pairs in the T2G and then singles in the T2G and singles in the EG for the high spin case. And then the low spin case would be 3 pairs and a single in the EG. So 3 pairs in the T2G and a single in the EG for the low spin case. Okay. So examples of something that would be D4 or D7: manganese plus 3, cobalt plus 2, chromium plus 2. Manganese CN6 3 minus, manganese CN6 4 minus, which is more likely to be high spin? Okay, so manganese plus 3 would be a 3D3, and then 4 minus would be a 3D, would be manganese plus 2, which would be a 3D4. And so being cyanide is a strong field ligand, you would not, you get 3D4. Okay, wait a minute. 4 minus, yeah. 3D4 would be 2 pairs and 2 singles. 3D3 would be 3 singles. I think I may disagree with this. I may think that MnCN6 3 minus would be the high spin case, because it had 3 unpaired electrons. I may have misanalyzed that one, but I'm thinking the 3 minus would be the more likely to be the high spin case. Okay, so now looking at the square planar complex. In the square planar complex, you're going to see the highest energy d orbital being the x squared minus y squared, because they point at the square planar points right at the x and y axes. dxy is actually next up because it's in the same plane, and then the dz squared is a little higher than the dxc and the dyz. For linear, it's the dz squared that's going to be the highest. Okay, so now looking at some applications of coordination of transition metal chemistry. First, in biology, we see a lot of metal ions coordinating with, linking to and releasing ligands to undergo oxidation and reduction. So this is actually very good in biology. You can use them as electron transfer, electron transport. They can be catalysts or drugs. So examples of this, chromium is important in blood sugar, manganese and various enzymes, iron in hemoglobin and myoglobin, and in the electron transport chain, cobalt's in vitamin B12, nickel is used in different enzymes, and copper is used in different enzymes, and also zinc is important in insulin and many enzymes. So iron is the one that we often think of because of plays a central role in living cells, such as electron transfer molecules in the respiratory chain, are iron-containing species called cytochromes. So they have a heme and a protein. So the heme has an iron ion coordinated to a complicated planar ligand called a porphyrin. These help us transport and store oxygen in mammals, such as myoglobin for storing oxygen and then hemoglobin for transporting oxygen. So those are examples of cytochromes. So this shows kind of the complicated porphyrin ligand, which is tetradentate, and it's surrounding this iron ion, and then that has the ability to bond to oxygen. So here we're showing the myoglobin molecule or myoglobin complex ion. Here's the hemoglobin complex ion. So these are very complicated, but they're similar in that they are complex ions with iron ions at the center. Iron is also important in steel production. So if we kind of go through the steps of making steel, you would start with some metal ore that you would, some iron ore that you had mined. There might be some pre-treatment, some reduction, some purifying, and then some alloying. So different ways to extract the metals from the ore are leaching, using some chemical solutions to dissolve the iron out of the ore. So you might leach it out by dissolving it out, maybe with acid, and then recover it by precipitating it. Some selective precipitation technique. This is also used in gold ore and aluminum ore. So your precipitation steps might involve various ions being used to precipitate out. The blast furnace is used to reduce iron to the iron from the iron ion to the iron metal. It's got a lot of different temperatures within the furnace that cause different reactions to occur. Also different chemicals like carbon monoxide and carbon dioxide and carbon are used. There's an open hearth method of heating up the iron to create the molten metal. There are different names we give to the different kinds of the iron: the molten pig iron, the scrap iron, and then a high pressure blast of oxygen is directed at the molten iron in order to oxidize any impurities and burn out any impurities. And then the exothermic reactions that are occurring are high enough to nearly boil the iron out. Doesn't completely boil it out, but it's enough to drive off the unwanted chemicals. Then you add flux to it. Electric arcs can be used to melt things and get the temperatures up, so electricity can be used. And this gives you higher temperatures than the open hearth or the basic oxygen processes. And it's even more effective at removing sulfur and phosphorus impurities. And you can add in oxygen to control the oxide impurities. You heat treat the steel and then allow it to cool, and that affects how it crystallizes into large or small crystals. And depending on whether your cooling is slowly or rapidly, that can affect whether your steel is going to be kind of soft and malleable or hard and brittle. You see the blacksmith. The blacksmith would heat the iron up very hot and then plunge it into cold water. And by plunging it, he's making it harder and more brittle because there's more cementite trapped, which is a kind of an arrangement of iron atoms in a crystal form. That cementite trapped cuts down on the malleability. The rate of heating and cooling is going to determine the crystallinity of the iron and whether the size of its crystals and how it's going to react to forces. Okay, so that wraps up chapter 20. So if you want to listen to this as a way of studying for the chapter 20 portion of the exam, it's available and will be available right after I load it up on the internet. Thanks for your attention.